Okay, intermolecular bonding is important in organic chemistry as it helps us understand why organic molecules have different properties. Now, up to now, a lot of the bonding you've heard about has either been ionic bonding, which is between a metal and a non-metal, or just the generic term intermolecular bonding. So if you understand that for a start, that there are different types of intermolecular bonding and how to tell them apart will help you enormously. Now, organic chemicals are molecules. They're discrete, individual molecules. So the attractions they feel to one another we call intermolecular bonding. And that's the attraction that you'd have between this molecule and another one. This would be an intermolecular bond, for instance. The bonds here are intramolecular, that's inside, they're just the covalent bonds. If these bonds are broken, this would no longer be CO2. So it's these bonds that we're interested in, the bonds that may occur between molecules themselves. This is an important point to make because if you ever talk about the bonds inside the molecule, an examiner would think that you're referring to the covalent bonds, and that would be inaccurate. You're talking about the bonds between separate molecules. Okay? Now the first type of bonding applies to absolutely all molecules. And there are different words or terms that are often used to describe this. The one that I tend to use in class is temporary dipole bonding. However, dispersion forces is one that's commonly used, as is London forces, and instantaneous dipole bonding can be used to describe this. Now, as I said, every single molecule has this type of bonding, so in any answer to do with intermolecular bonding, you do have to appreciate that all the molecules you're dealing with will have this type of bonding. It is the weakest form of bond, and describe it now. Okay, now last year in year 12, when you looked at, for instance, this is supposed to be, I've left out the electrons, it's not a proper Lewis diagram, just showing really just two oxygen atoms with a double bond between them, and you're used to thinking of these electrons in here being shared equally, and the electrons that would be on the outside staying in fairly fixed positions. Again, this is just a Lewis diagram, this is not how they'd really be. We're kind of used to thinking them of just being in the same place all the time, and because we'd consider this to be a non-polar molecule, that the electrons in the middle wouldn't move one way or another, and there would be no polarity, and therefore we'd consider that to be non-polar. Now what actually does happen is the electrons aren't just staying in one place, and at different times they can move to be either more towards one side of the molecule as a whole compared to the other. And for instance, if we illustrate that with this purple being the electron cloud, and if that moves more over to the right, we would get a slight negative charge. This funny little symbol I'm doing here, that one, is the Greek word symbol for delta. There are two symbols for that. If you remember, this one is another one. That's kind of like the uppercase. And so this means this would be slightly negative and this would be slightly positive on this side if that happened. And this happens in an instant, which is why they're sometimes called instantaneous. And they're not always, it's not always going to be like that. So that's, why it can be called a temporary dipole bonding. The term dipole simply means that there are two poles. There's a negative and a positive, but this is not a full negative, it's not a full positive. This is not an ionic bond. Ionic bond is when an electron has either been gained or lost. This is just the electron cloud being more to one side. It's a slight negative and it's a slight positive, not a full negative or a full positive charge. Okay. Now when that happens, if on the other side we have a similar positive charge, it's going to be attracted to the negative. And again, I shouldn't really use the word charge, but it's a slight positive and a slight negative, we'll get an attraction. Okay, it's a fairly weak attraction, and this is the temporary dipole bonding. And we would see the same thing, for instance, below in a methane molecule. We may get in here a bulge going to one side more, and if that happened in this whole molecule, we'd have a slight negative on one side and a slight positive on the other, and that would then be attracted to another molecule. Okay, now the one thing with this is, even though it's a weak intermolecular bond and it's considered to be the weakest of the three, it's completely related to the size of the molecule, the size of the electron cloud as a whole. And so we're not just talking about the valency electrons, we're talking about all of the electrons. So generally, so it leads us to one kind of common thing with temporary dipole bonding. The larger the molar mass, therefore the more electrons, the stronger the temporary dipole will be. So even though it's considered weak, in large molecules it becomes a significant factor in determining whether it's going to be a solid, liquid or gas. Okay, so that's temporary dipole bonding. Now, in an oxygen molecule, the only type of bonding that's going to exist is going to be temporary. Okay, now one way of imagining this is thinking about polarity, because this would be a non-polar molecule. HCl, though, we'd consider it to be a polar molecule. Chlorine has got greater electronegativity, greater attraction for the electrons in that shared bond. Therefore, we'd get a slight negative and a slight positive. So using the same slight, this is not an ionic bond or case, therefore it's just a very slight negative. But unlike temporary dipole bonding, because chlorine is more electronegative, this is like this all of the time. And one way of thinking of it is, if a molecule is polar, if it's polar, it will have a permanent dipole. So this is considered permanent dipole because it's a dipole because there are two poles. There's a negative and a positive, and it is there all of the time. Okay, whereas with temporary dipole bonding, that can change. This could be negative and positive, and that could change. Okay, and it's instantaneous. It happens in an instant, and it's dependent on the electron cloud and which way it tends to be, either to one side or the other. So anyway, permanent dipole bonding is just based on that difference in electronegativity. But as we're talking about bonding, we generally don't need to talk about polarity. You may mention it, but when we're talking about bonding, you should use bonding terms. This is a permanent dipole bond, okay? And they're fairly easy to recognize. You just have to be able to identify if there's a difference in electronegativity between two atoms. Now, the last one is hydrogen bonding. In some respects, this is just like a permanent dipole, but it's a special case because it's especially strong, and that's because the difference in electronegativity is especially large compared to normal permanent dipoles. If you look at the periodic table, nitrogen, oxygen and fluorine are in the same period, and fluorine is the most electronegative atom. So oxygen is also very electronegative, as is nitrogen. And what we find is when any of these three atoms is bonded directly to hydrogen, we have an especially strong intermolecular bond. And this is related to the fact that as soon as the electrons are pulled closer to nitrogen, so they go this way, so we'll get a slight negative and a slight positive, hydrogen only has one electron and one proton. So when they get pulled over, effectively this leaves a proton unshielded. So that happens in each case. So it's an unusual case in that these are very electronegative atoms, and hydrogen only has one electron, so when it's pulled towards something, it makes it fairly unique, and it makes a stronger bond. And because fluorine is the most electronegative, this would have the strongest hydrogen bond, then oxygen, then nitrogen. Notice this is just the same order in terms of as we go across that row in the periodic table. You should be able to recognize these bonds and what they mean. Okay, if we look at these different molecules, these are just kind of structural drawings, and not Lewis diagrams or anything like that. If we look at H2O, obviously we have, if we were to consider the kind of bonding that must be present in this one, we're always going to have temporary dipole bonding. It's present in every single case that's on this page. They're all molecules. We also have an oxygen bonded to a hydrogen, and that means we would have hydrogen bonding there. Okay. In the second case, we only have nitrogen bonded to nitrogen. Therefore, the only bonding that's going to be present is going to be temporary dipole bonding. Okay, there's no permanent dipole. This is a non-polar molecule. Okay. In the third case over here, we have an aldehyde, and we've got a carbon bonded to a hydrogen. Now that's, remember, effectively non-polar. The hydrogen isn't bonded to a oxygen, nitrogen, or fluorine. Therefore, there is no hydrogen bonding, but there will be temporary dipole bonding. And because of this here, we will get some permanent dipole bonding. There would be a slight permanent dipole there because of the difference in electronegativity between the carbon and oxygen. Okay. Now the fourth case, we've got temporary dipole bonding because it's present in every case, and we've got oxygen bonded to a hydrogen. That's what that's supposed to be there, and that means we would also get hydrogen bonding going on. Okay, so that would be an attraction between this and another molecule over here of a similar type, right? That's what would happen in that case. And number 5 here, we would see there's a temporary dipole bonding, but we've got a nitrogen bonded to a hydrogen, so once again we would get hydrogen bonding going on here. Okay, now just to give you a better idea, these are just supposed to be 2 molecules of ethanoic acid, and I'll just try to show some of the slight charges that may appear. Now because of that, negative there, we're going to get that attraction between those two and those two. And in fact, this carboxylic acid is unusual in that it can do something called, this kind of dimer bonding where there's 2 of them. Okay, so it's dimer is the term I'm using there. And this is a hydrogen bond here, because, and now it's important to realize the hydrogen bond is not here. It's the oxygen bonding to the hydrogen that creates this charge that results in this attraction in here. This middle part is the hydrogen bond here. This one here. This is the hydrogen bond. It's this dipole here that creates it, but that's the actual bond, the attraction between this and this molecule on this side, this whole molecule. So anyway, now just to clarify, in carboxylic acids, I'm not ignoring this oxygen here. In fact, because of the double bond here and the electronegativity of the oxygen, this is a significant dipole. It's very highly polar. Not as much as a hydrogen bond would be maybe, but the actual hydrogen bond, the actual bonding occurs between here. Now this H bonded to this O creates such a dipole that has the capacity to hydrogen bond. This is the actual bond here though. So I'm really just trying to point out the role of this carbonyl group, which hasn't been ignored at all. If it was there and there was no OH and it was bonding to another molecule, it would be permanent dipole bonding. Okay, now if we look at these different organic molecules, which one would have the highest boiling point? Well, the one that I just drew previously, carboxylic acid, that has the ability to temporary dipole bond. It also has the ability to hydrogen bond, and that's due to the oxygen and hydrogen in here in particular. But it can also has the ability to bond at 2 different points there, and that creates a special case. If we were to go for the next one, we've got 2 molecules, this one and this one, one's got an alcohol group, the other's got an amine group, and I forgot to put another H on this one, just put that in. How would these differ? Well, they both can have temporary dipole bonding, and they both have the ability to hydrogen bond, but the alcohol would have a stronger hydrogen bond because oxygen's more electronegative. It wouldn't be significantly different, I wouldn't imagine, but that would be a consideration as well. And if we look at the last two, we've got the aldehyde, which would obviously have the ability to temporary dipole bond, but we've also got this group here, and that means it would have the ability to have a permanent dipole. This does not have the ability to hydrogen bond with other molecules that are the same as it. Okay, and here we have a normal alkane, propane, and that would just be temporary dipole bonding. That's the only kind of bonding it can do. Now, the important thing to keep in mind is that temporary dipole bonding, even though we consider it to be weak, and so for instance in ethane, it's a gas because, well, it's only got temporary dipole bonding and it's a small molecule. But as we go larger to molecules such as octane, and if we were to draw in all the H's on this gets to be bigger, and it's a bigger molecule, therefore the temporary dipole bonding becomes stronger, and instead of this being a gas, it's now a liquid. And the fact that it's a liquid tells you the bonds must be stronger. Okay, it must take more energy to break. It's going to have a higher boiling point and a higher melting point. But that increase in strength of bond due to the size of the molecule can be very, very significant. So in NCA, it's important when looking at any questions to do with bonding to consider the size of the molecule. And if it seems to have an unusually high boiling point and it only has temporary dipole bonding, it's probably the size of the molecule that's important. Okay. There are some other factors that we do look at in bonding, and those are to do with packing. A linear chain like this, I'm not showing the H's, I'm just showing the carbons, that can get closer to other molecules that are the same as it, and therefore, because it can get closer, its bond will be stronger. So this is more of an excellence type understanding that we do consider temporary dipole bonding and the size of the molecule. We do look at permanent bonding, permanent dipole bonding and hydrogen bonding. But if things are still a little bit hard to understand and why something has a different boiling point, you need to consider one last thing: its ability to pack together, its ability to get closer to the other molecule. And this one with branches, that's going to be harder for it to get closer, and it's going to be more awkward, so it's going to have a lower boiling point or melting point, a weaker bonding. Okay, it's one last thing to consider.